All right. So I'm Carolina Caetano. I am officially the instructor of this course. It is a matter of bureaucracy in the university that it is very hard to register the courses as a double, but then, everybody knows from the grapevine that these courses are taught in that way. And the way we do it is we divide Greg's parts by his parts are more applied, my parts are more theoretical, which makes a lot of sense because I am a theoretical econometrician, he's an applied econometrician, and so you get the knowledge from people who do this for a living and are passionate about it. I'm passionate about theory. Whenever I had to teach the practical part of this, it was fine, but it's not my passion. And he's the opposite, and so I think that's pretty cool in a sense. And, because when married, there's a lot of internal communication that is like better than normal, and so that's cool, sure. So Greg, of course, has explained the course, and so what we're going to do is we're going to start going into the theory of all these things. So let me see if I have anything that I want to tell you before in advance about the general level of this. Well, okay, let me just say something quickly, just so that we don't jump like crazy over this. So remember this course and also the labor course that comes before, which is not properly labor, by the way. I highly incentivize anybody who wants to come to that course to come. It's really not a labor course. It's more like a technique course, which is covers techniques that are complementary to this course. This does not cover any of the techniques that are here and covers techniques that are not covered here. So it is courses that are there. There's a partition there. You're not going to learn the stuff that's learned there, here. Not at all. There's going to be minimum intersection that I might have to like redefine a variable or something. Overall, definitely different topics. And so, that's something to know. So here we're going to be talking about is the classic, currently considered gold standard of causal research in economics, which is the design-based methods. So the methods that rely on some natural thing that happened that simulates an experiment. Now, of course, by studying something like instrumental variables, you are also studying experiment theory. So a lot of this course is experiment theory. So if you were to actually run experiments in any field that's done, this is good knowledge too. But I'm going to teach it with the language of instrumental variables because then it covers both types, which is the actual experiments that you run on a lab or some form of, somewhere that you convince the government to do something, or but also covers the natural experiments that happen in the world and things like that. So we'll study that, and then we'll study regression discontinuity designs, which are very similar conceptually in a sense, but very different phenomena. And they have a lot of particularities and a lot of details. And so we're going to study those quite in depth. And that's the whole point of this course. And this is why I incentivize you to come to the other classes of you that have some curiosity or some ambition, because we're going into some modern things in that course, which are question-based types of approaches, which is a world where you have a question that has to be, that you want an answer for, and then you would like to answer the question, but there is no experiment, there's no natural experiment, there's no way to answer it like that. And as Greg will show you, there are actual examples where it is actually impossible to answer them with IV or RDDs and things like that. And then there are new things to do. The world of answers for this type of issue, so the world of approaches that are just question-based, that in environments where you don't have those types of randomizations, is very limited, but they exist. And so we're going to teach that. They're technically much harder, but then again, the payoff is higher too, because there is buckloads and buckloads of free questions all around. I have a student from ARE, I think it was ARE, and she did a thesis actually on one of those techniques, in the past, having learned it like that as well. So it's not just economics that we use this technique. She took great advantage because she was like super pioneering in some of these fields that are just appearing. But it does take a certain spirit because these things are harder and they are really expensive. So here we're going to study very well-established techniques. I say they are the gold standards because they're generally seen as that. Now, the reason they are the gold standard is because in theory, you'll see when I show you the theory of them, they are truly the cleanest possible way to approach this. When you look at the conception of what instrumental variables are like or what RDD is like, you're like, oh, this thing is like perfect. Conceptually, it's so beautiful. But you know what? The practice kind of sucks. Let me just warn you right away that the reality of IV, especially, but also the reality of RDD, there are very good RDDs. But the reality of IV is very messed up. And the reality of the majority of the RDDs is kind of messed up to very messed up, somewhere around there. So these techniques in practice are a lot worse than what the theory looks like. And in contrast, the kind of stuff that we're teaching in the labor course, they are in practice substantially better than what the theory predicts. That has been our experience having worked in applied and theoretical research on all of those. I have now, I think, written on every single area of causal econometrics inference. I think I've written all of them. I literally have written papers on every single one of them. Different RDD, IV, bunching, and also like just pure like type matching kind of stuff. I've worked on every single one of them. And Greg has worked in applied work, I think, in every single one of them as well. And so with the gamut of our experience on that stuff and tons of simulation, I am flabbergasted at the reality of these techniques in comparison to the reality of the other techniques. But the theory does not look like it. So there is sort of a market imbalance in which these things are considered golden standard. And yet I'm like, the reality of this is not right. By the way, this is true of experiments as well. You know, when you go and study experiments, with the exception of vaccine research and sometimes medication research, when you have proper placebos, with the exception of those, you'll be surprised how much like experiments are also messed up. There's so many problems there. The reality, you're like, I'm not sure that this is proper scientific knowledge at all. But again, a little knowledge is a very dangerous thing. So don't go with my statements here and now become nihilistic and nothing is good and there's no good knowledge to be had. That's not the call. The call here is different. The call is more like, you need to know more. So this thing, you need to go deeper. You need to know way more. So we'll study these techniques. You need to know them. They're basic formation. You're very likely to come across them. If you can get a good design of some of those, excellent. You're gonna get, good thesis, good publications. They still sell very well in the market. But the biggest, the more likely scenario is that you're gonna operate with them at an imperfect level. So you need to know the basics, you need to know the perfection, and then we're gonna try to go into the imperfection and give you like whatever we can give you. And then a lot of that you have to kind of do on your own. But that's the more likely scenario thing I envision for anybody that's gonna go into research it's gonna go into academic work, which is kind of like what grad school is designed to resolve. We design grad school, especially in economics, with the intention of going to research, right? So that's kind of what we think. Some of you are going to go into think tanks and work for the private sector, but you're going to work with research anyway. And so that essence is still going to be useful and important to know. So think tanks, people work for the government, so the Fed and those types of institutions also use those techniques. So there is quite a bit of, even going far away from academia, that these things are still useful. But they do become substantially less useful as you move away. That's for sure true. So for example, in academia, IV and RDD are going to be way more run-of-the-mill than they're going to be in companies. Then again, in companies, you might do a lot of experimentation, which IV is useful for. So I don't know. Okay, so that's the end of my motivational talk. And be motivated. Be motivated. Are you motivated?
Yes.
Are you already motivated? Yes. Okay, great. Okay, so let's start the material. So what we're going to use here is the potential outcomes notation. Now, in the previous class, we had a long and very difficult, we could say, philosophical discussion on the nature of this thing, which is cool. And it's really a complicated object, much more complicated than it might look. But you know this already to a large degree, because I'm sure you've seen it, right, in prerequisites and things like that. If anybody has not seen it, you should know it is part of the prerequisites. You need to catch up fast, because I am going to move as if you already understood this object in this course. And so you should have seen it a lot in 8080, for example. That's used up and down all the time. So we are just reviewing very quickly. This is the potential outcome, and it is, let me just move the board so that we have a proper recording here. So that'll be 3, all right? Okay, so we have the potential outcome, which is a sense of it is a notation for what would be a counterfactual. So the idea is that every person has inherently a bunch of outcomes that would correspond to different types of treatment. Now, those things exist. So we imagine that for every person, there exist values that they would have had they consumed 0, 1, 2, 3, whatever D is. So D being the treatment. And so there is then a set of counterfactuals that are defined and inherent to the person. And then the person then goes on to consume whatever it is and then receives the outcome that corresponds to that level of treatment. I'll tell you that mathematically in a second. But the idea is that this object is well-defined and understood. Are we good with that? Are we cool with that? So more philosophical understanding, much, much deeper understanding, you will need to have gone to the other class or perhaps watch that other class that has been recorded. Unfortunately, imperfectly, because I made some mistakes on the recording. So don't be weirded out if like a good part of the class you're staring at a whiteboard because I literally pressed the wrong button. So I'm sorry. But I'm saying things and eventually I do show the board of what I'm saying. But you could catch that discussion if you're interested to see the kinds of things that are happening in the other class. But the idea is that this object is actually a lot more complex than you think. But in this class, we're going to imagine that you kind of have some understanding of it. The most important piece of that object is that we can write the following relation, the following identity, which is yi of di equals yi. And what do I mean by that? Oh, by the way, I didn't say that, but the treatment is going to be di. I imagine that you're also used to that because that's what is normally used in diff and diff, and you guys have been studying that before. And so D is going to be our treatment. As I said in the last class, I don't like D because D is great when you have binary treatment. D stands for dummy, so 0, 1. But it is very bad once you go into multi-value treatment because when you get to multi-value treatment, we're thinking of things like derivatives. And dt is the worst thing ever. Dt, what are you talking about, right? So I would like an x, so I do dx, these some derivatives, d. So you know what? D expected yi of 0 given di equals d, for example. It's a normal object, to work with. dd. That's so bad. We might have to work with something like that. Hopefully not in this class. So the people are going to suffer as the other class. But I don't like the d, but we deal with it. In this class, we're going to do mostly binary treatment. It's going to be 0, 1. Only because that is what the theory is done for. You'll be shocked how little theory and knowledge there exists of instrumental variables and RDD for multi-value. It's like incredible. It is extremely little. By the way, same for diff and diff, actually most of economics. Very little knowledge. It is very little that is known. And it's not a coincidence. It is very hard. It's actually very hard to go multi-value, but it's very necessary and is the reality of most actual treatment. So I am going to see if we can get into some of the multi-value, but very little is known. So most of what we're going to do is going to be binary. So this is going to fit well here. Now this identity, that's a good word. That's what I wanted to say. So this identity is fundamental. It's going to be on the math everywhere that we do. And what it says is that the outcome you actually get is the counterfactual corresponding to the treatment you actually get. Does that make sense? So this seems like so sort of obvious, but it isn't because it is making a statement of two very different things. One thing is the outcome as you have it, like the realization of your outcome. A different thing is a counterfactual notion that existed before. It existed as an inherent thing to you. Well, that thing, had it been applied to the treatment you actually got, that is exactly what you got. For that to be true, you need several conditions, which are the several conditions, which are not in this class. So I'm going to erase them here. Sorry, need to watch that video and then go to something else. But they're actually rather delicate. And in this class, we're just going to assume they're all satisfied and that this particular identity holds. If that identity holds, then we can do all the math that we are going to need to do. Does that make sense? Is this, so far so good? Okay, so that is our object. Di is our treatment. Di, of course, represents a random variable, which is the actual treatment realized, right? So the actual treatment. And then little t, it stands for like a theoretical treatment. So it's also treatment. I don't even want to write, but it's sort of like a theoretical. I'm just going to say theoretical treatment. This is not an official name, but I'm going to do it. Theoretical treatment. What do I mean by that? I mean that it's a standing variable for us to kind of like impute anything. So we would say, if you were what? If you were zero, if you were what? Sometimes we're going to just do y of zero, y of one, but sometimes we do y of d to just represent a given, right? So basically what it is. So it is theoretical at the essence, the I is the actual realization, and so on. One little detail, which is not that important for this class, but I'm going to say it anyway. Yi of d is a function of d, which is a deterministic function per person. So the idea here is that everybody has exactly one possible reaction to every treatment level. So it's a function. So I have yi of 0, I have one value only. The other person has another value only, deterministic. Now, the randomness comes from the fact that my sample is composed of random people. So the randomness comes from the population draws. So from the draws from the population, that's what's random. But every person has their own function, which is deterministic. Is this realistic? I don't think so, but it's good enough because it works well. So it works well enough that it yields proper results, and so we're going to be fine. However, one thing that we're going to do in this class is acknowledge the fact that different people have different treatment effects. So in this class, we are going to be, in both classes, by the way, we're going to be acknowledging the fact that treatment effects may be different from some person or another. So treatment effects will be heterogeneous, right? So you may have a different one from another. But in this, we're not going to fix it. Like we're not going to go and actually figure out treatment effects for subgroup very much, but for like specific people. But we are going to at least acknowledge and do math then. Does that make sense? Is this okay? All right. Okay, so let me see if I have to say anything about the setup. I think this is enough. Okay, and so the first thing I am going to show you, let me see if I go to the second board. The first thing I am going to, because I don't like this space is too little for what I need, I'm going to just erase this. So that was a bit much. The first thing I'm going to show you is the reason why we're doing things and the basis of everything we're going to do from now on, and that is the fundamental problem of causal inference. And the fundamental problem of causal inference, actually, let me tell you about it first. So the fundamental problem of causal inference is the problem that we don't have a time machine. That is the problem. It's like we have a fundamental problem because we don't have a time machine. What am I saying? The fundamental problem of causal inference is the fact that you cannot infer causal effects because the counterfactuals are never observed. Whatever it is that you actually did, what would have happened if you had done something else is not really observed. It's not really within the realm of things that we observe. Let me just see if you can see. Yeah. Okay. So we never observed that. So if you consume, so you came to grad school, y of 1, let's just say, you're going to get the outcome of somebody who came to grad school. We're never going to know what your y of 0 would have been had you gone. Why? Because we don't have a time machine. Now, the classic solution for that problem would be that we don't go back in time. We just get somebody who's comparable. So we're going to get somebody who is exactly like you in every possible way, and that person would not have gone to grad school. You have gone to grad school, and then we would compare them. The problem is that is just as impossible as going back in time. There exists nobody who is truly the same as anybody else. That includes even identical twins, because even identical twins have different life stories. Like they have some different experiences. And so it is true that twin studies are some of the best things we have. But honestly, they are still fraught with issues because twins don't necessarily have the exact same life. And so the reality is that we don't have that. That second possibility is also out of the realm of things we can do. The solution has been always, so far, no, that's a wrong statement. The solution has been, before we knew better, we knew more, to have security in numbers. The idea being that because of the law of large numbers, and the law of large numbers is for means, but you can do it for every, you can basically, it holds in some sense in distributions. But the fact is that if you randomly draw from a distribution, sufficient number of observations. So if you draw a lot of observations from a distribution, then the resulting group is going to look a lot like the original. And if you draw two groups with enough observations on each, they both are going to look like the original distribution, which therefore means that they're going to look like each other. So because of that property of random draws, that they're going to look like the original and therefore they're going to look like each other, you're going to have some form of comparability, meaning nobody's equal to anybody else, but as a group we are, in every way that you can describe it. So we are not really equal ever, but in any average, any moment, any variance, any whatever, any aggregate measure, we are like each other. And that turns out to be sufficient to get some causal effects. Now, it is very funny when you think about, is this sufficient to get some causal effects? Because the only reason we think this is sufficient is because we believe it is sufficient, because there's actually no proof that it's sufficient. There's no proof because there is no way to mathematically define causality. There's no like actual definition of causality that says, ooh, then it is causal. But you know that if I went back in time and I made you do something else, that difference would have been the causal effect, right? You know that. You would like, yeah, of course, right? Am I, please do this. Like, you get it, right? So I say, hey, you went to grad school. If we could have gone, I'm going to do this mental, this mental mind experiment, how do you say it? Mental experiment, in which I tell you, hey, if we had gotten back in time and made you do something else, and we compare the outcomes, we would have discovered the causal effect. And you would say, of course, right? Yeah, that's obviously, yeah, they'll be like, yeah, then we will know the causal effect. And okay, but we can't do it. And I said, okay, if we had gotten somebody just like you, and then had made them not go to grad school, we would have, and compared your outcomes, we would have gotten the causal effect. You would say, yeah, right? You agree with me. There's no proof, you understand? Like, we get it. We get that this is true. Well, it's not different with experiments. I tell you, if I get two groups that are similar in every way, except this one thing, and I make this one group do something different than that group, and it's just one difference. The groups are untouched, they're equal in principle, drawn from the same distribution, equal in principle. And then I do one thing to one group and don't do anything to the other group. That's one difference. Then the comparison of the outcomes of the groups in an aggregate manner should give you the average differences in the average causal effect. And you would say, right? Yeah. But remember, there's no mathematical backing to this. This is just something that we're like, oh, yeah, that should work. Right, so that's the idea. It's just a little side here, okay? Because everybody thinks, oh, this is the gold standard, But the gold standard stands on things like the things that we talked about in the previous classes. Very complicated in reality, but there's nothing mathematical that makes an experiment work as a real way to get causality, other than the fact that we're all like, yeah, of course, this should get the causality. That's basically what it is, which I think is kind of interesting. But anyway, so that the idea, therefore, is that if you can get two groups from a same distribution that look sort of randomly being drawn from this distribution. And by the way, there's nothing inherent. No, let me just finish this thought. So if you get those two groups and then you do just one level variation, then you would get the causal effect of that level of variation. We agree on that. I said a lot of words, man. I said a lot of words here, and all these words are going to come back one way or another into the theory of what we're going to do, right? So it's like, drawn from the same distribution, perfectly comparable, modify just one thing. That's like a lot of little things hidden in there, right? That's a lot, right? Seems very simple. You're like, yeah. There's like 10 things in there that we need to be very careful about. And guess what? They're more often than not satisfying scientific research. With the exception of, as I said, medication research and when they have placebos that are very good. And then when you have vaccine research, pretty good that way as well, because they have like so much control, because they can control who's going, because they know who is given to, right? So vaccines, you observe if they took it or didn't take it. So there's nobody that can like, oh, I'm going to decide. And if you show up for that, they're going to inject whatever it is that they're going to inject. So they have good characteristics there. So with the exception of those, man, you're getting into a whole lot of the little things I'm talking about here. Right? A lot of these things are going to be under discussion. We're going to discuss those details as well. Okay, so that's basically the foundation of what we're going to have here. But and I'm going to say this, I want you to pay a lot of attention to this. The base of causal identification is not randomization. It is not because I randomize. I mean, at the essence, yes, in the sense that let me just say this to the end. The reason why everybody here is like, yeah, that's causal, is not because I randomized. It's because they're comparable. Comparability is the basis of our willingness to say that they are comparable, that this is causal. Is the fact that I said they're equal in every way, and therefore they, and I just changed that one thing. So the two things that went into it, they were comparable, and then I changed just one thing. Those were the two things that actually convinced your brain. When I say randomization, you may be used to having connected randomization with that characteristic, but we can drop the randomization part and still have the comparability. And if you have the comparability, that is enough. And that's very important here because the examples we're going to be talking about, they don't really have randomizations. So some do. Okay? There are some cases where the government has randomized something. But in many other cases, we don't really have a randomization. We just have the second part in which we're like, no, but they're comparable. Something like a very quick before and after. So I have a population that here they are one day, and then the next day something else happened. And then we see like how something varied. I mean, come on, one day, what's the difference? I mean, for every person, huge. But as a group, what was a day? I mean, if nothing really huge happened in the economy or something like that, or like in the world, what is one day between a group and another, a group today, another group tomorrow? It's nothing. In group, right? Every little person had something happen, but as a group is whatever, right? So it's just very comparable. No randomization happened. And yet we're going to be willing to make comparisons because we're going to say, come on, man, they're the same group. They're super close in time. Like they're the same, they're very comparable. They're like, they're two groups that are like, in principle, kind of like, there's no reason why you would think they're different. It's just one day was the problem, but they weren't randomized. But we're okay with that comparability thing. Then you see, and then we're going to accept the type of causal inference. RDD is actually even more interesting because there's definitely no randomization there. What happens is that people are like around the threshold, and then you have some people are before, some people are after. In some sense, we can think of them as random, but there's really nothing random. They just took an exam and then got some result, and then the result they were sorted somewhere there. Remember, we're thinking that the yi of them is not random, so they were just sorted into that place, and there was no randomization, and yeah, we're going to say causal. And your brain is going to be like, yeah, of course this is causal. Why? Because you have comparability. Remember that little principle. The basis of causal inference is comparability, not randomization. And I'm going to even say to you that that's not even true, right? There is now technology that can establish causality without comparability. So comparability is not really at the essence of causality. There is even deeper principles that are satisfied by it. But to this day, the immense majority of techniques, and up to the other day, it was all comparative based. You're making that face. I'm going to tell you in a second, what is that? You're like, what would that be, right? That's kind of like what you're like, what would that be? I'll give you in a second. I'll tell you in 1 second because you're going to see. And you're going to see because I'm going to show you the fundamental problem of causal inference. And so let us now talk about the fundamental problem of, oh, by the way, the fundamental problem of causal inference, I told you, is the not going back in time. That's at the base, right? But you can also say the fundamental problem of causal inference is not having a comparable group. You could say that. Those are all sort of like incomplete versions of that. The fundamental problem of causal inference is defined on a case-by-case basis, but it does have to do with the fact that you always have a sense in which it's almost tautological. You always have a sense in which it is problematic to define causal inference. So let me give you that a second. So I'm going to show you that in the basic case, which is we're going to compare two groups. So if I'm going to compare group one, let me see if I have the camera in the right place. Maybe get it right there. Okay. I'm going to compare group one. So I'm going to look at the expected outcomes for group one. What am I saying here? The object here is the outcome. That is the mean outcome in the group that has gotten treatment equal to 1. So we're going to call this group the treated group. The group was treated. I don't know, they went to grad school versus not going to grad school, something like that. I'm going to compare them to the group that did not go to grad school. Now, what is the problem here? Let's use potential outcomes notation. So that's our first encounter with math operations, which are going to use that particular equation, and we're going to go from there. Okay, so that the identity that we talked about. So that is basically the expected outcome of bi of one, or so I'm going to just do bi here. Bi, I'm going to go slower. Given bi equals 1 minus expected yi of bi given di equals 0, right? So that's basically just saying the identity has been used here because it has been satisfied. Now, what is the outcome of di when di equals 1? Is the outcome of 1. So I'm going to rewrite this now to the expected yi of 1 given di equals 1 minus expected yi of 0 here given di equals 0 because these people have consumed 0. I'm going to talk consumed when they were treated for no good reason other than it's convenient, but it's definitely not a general rule that we're talking about consumption things, right? But sometimes it's just useful. Now, what I'm going to do next is a classic trick of econometrics. Learn it immediately. Whenever we do any econometrics anything, we always do this particular decompositions in which we add and subtract something. So adding and subtracting is the bread and butter of econometrics. Every econometrics paper begins in some way with something like that. So I'm going to do, in fact, the one I'm going to do is going to be about the most used of all of them, which is we add and subtract yi of 0. Why? Because y of 0 is the baseline. It's like what would have happened had you not done anything. Because we tend to consider the treatment as the thing you do and the non-treatment to be the kind of baseline. So because we like that, which is by the way not really true in every example. But sometimes the treatment would have been stopping so these kinds of things sometimes will change size. But it's fine. So it just makes some sort of sense. And so we like to add and subtract y of 0, which is what I'm going to do next. So what I'm going to do here is I'm going to do expected yi of 1 minus yi of 0 plus yi of 0 given di equals 1. And then I'm going to continue to subtract expected yi of 0 given di equals 0. Now, you may be thinking, why did you subtract y of 0 versus y of 1? Like, why did you do this thing with y of 1 instead of y of 0? Why did you do it here instead of there? Because I know better. Because somebody has been trying this stuff and figured out that this is the way to do it. To be entirely honest with you, we could have done this in a number of ways and examined this in a number of ways. But the profession has been doing this for a long time in this particular order. Therefore, we have language for this, we have understanding for this, we have so much for this particular order of things that it's just worth it to just step on the shoulders of giants rather than kind of rebuild it. But there exist things, you're going to see that we're going to get to something like ATT, which I'm sure you have heard about, right? Average treatment effects on the treated. Well, there is such a thing as ATUs, which is average treatment effects on the untreated. And that is actually a different decomposition than that. So all of these things exist. It's just that I'm just going to go the way that most of the time we go, because that's how we like to think. Once you have thought enough that way, the rest becomes extremely easy. You could have just done it. But you see what I mean? It's just easier for us to think in the way other people have thought, because then we have language, we have everything. So I made that decomposition. So the answer to why did you do it like that? Because I know where we're going. So it's not really a fair answer. There's no real reason other than I know what other people have done and where we have to get. You could have gone differently. And everything will go through, except with different language. You have to think through stuff. Things are going to look like what you want to get. But in truth, everything is right. And it was going to work. But good luck. So let's just do it the way that we know they have done. And by the way, a little trick of why did I go that way here in particular? Because I want to get a treatment effect. And y of 1 minus y of 0 is a treatment effect. Let me get there in a second. Let me just finish that decomposition. So I'm going to bring this term out, and I'm going to go expected yi of 1 minus yi of 0 given bi equals 1 plus expected yi of 0 given bi equals 1 minus the expected yi of 0 given bi equals 0. Are we good? You, by the way, ask anything that looks weird. The notation is not like you can't read what I wrote. So I have no shyness about this. But we're good, the composition, right? Everybody, please. I want to see the nods. We're good. Okay. So, because that way I can move on. Okay. So, do we all agree that this is the treatment effect? Again, this is just mathematical notation that has like no real backing. It's just denoting something. But what is it denoting? It's denoting what would have happened if that person had consumed 1, and what would have happened if that person consumed 0. Well, that is exactly the going back in time. So I go back in time and or the two equal people, right? So I'm saying, if you had gotten 1, what would have gotten, you gotten 0, and now compare it. That is a causal effect because we said so, because we believe that that's what it is. So it's basically just standing in for that. So the comparison between two counterfactuals is the causal effect. Why? Because we said so, because we believe that that's the case. Right? Once you define counterfactual, causal effect becomes an obvious thing. Or once you define causality, then counterfactuals become an obvious thing. But no matter what, we just said that. You get the sense you get what I'm talking about? So the people who have been in labor gets it a lot better because we talked a lot more in depth about this. But there is a sense in which, this comes from a belief, let's just say. Okay, so this is the treatment effect for person I, and that is among whom? Because this is the average treatment effect of person I, but I'm getting a mean in a subgroup, conditional mean. So that is a mean among those that consumed 1. So among those that went to grad school. So that's going to be, let's say, wages. So that's going to be the expected treatment effect, so expected increase or decrease in wages from having gone to grad school among those that did go to grad school. So that is a very specific form of average that we call the ATT, average treatment effect on the treated. So I'm going to go ATT, that's average treatment effect on the treated. Now, I love average treatment effect on the treated because if you look at that equation, it comes exactly in the right order. Average, everybody eyes forward, average treatment effect on the treated. So it's 3 components here. So first thing to realize, this is a treatment effect. Why is it a treatment effect? Because it is so what we're going to call treatment effect here in this course is like any average of treatment effects. And by the way, any average that is like positive weights. And by the way, any average with the weights average 1. So this gets very hard. So let's wait for more details on this as the course progresses. But the idea is that is this some none of this stands on math, but is this in some sense that your brain can conceive a proper thing that we can think of as a treatment effect? I think the answer is yes. So, and I'm going to tell you why, and then I want to see if you agree. Because right now I bet you're like, what are you even talking about? But let me just change the camera here a second. So, no, this one. Okay. So, is this some form of treatment effect? Yeah, because it's like a mean of treatment effects. So, I mean, it's not really a treatment effect because it's not the treatment effect of anybody in particular, but it's a mean treatment effect. So, in my mind, that seems like an acceptable object of study, doesn't it? Doesn't it seem, like I said, right? That's sort of the sense in which we're working with it. It's not really the treatment effect of anybody, but it's the average treatment effect on a group. And that is something that we can definitely talk about in science. It corresponds to something that humans will get. Like I say, hey, if you actually give an incentive for people to go to grad school, that's what you should expect to be like the average effect. So that I like this. This is something that, my brain thinks this is useful, right? We're good? Now, there's a little caveat in which it is in a specific subgroup, which is the people who do go to grad school. So there's a little caveat there, right? I would have liked the average for everybody, or maybe not, I'm not sure. But I do know that you just wanted to call their attention that it is in a specific subgroup, right? It's a subgroup of the treating. Not a big deal, very excellent object, would love to get it. Are we all in agreement with this? So that's a causal effect and breathe. But it is, again, Remember, it is again an average and it is again on a subgroup. So little detail, we already start this from compromises. Because what I would really like is what would have happened to me, what would have happened to you, right? What we would really like is our own navel decision, right? I would like to stare at my own navel and be like, what would have happened to me? Most decisions in life, if not, well, with the exception of the government, I guess, or a company or something like that, most decisions are taken on an individual level. You decide where you're going to put your children. Like most of the decisions we take on a daily basis are of an individual nature, which is things about you, about your family, about things like that, right? So it's interesting that we already start, the whole technology that exists already starts from that place. We know very little as you try to get at the individual level data. You should know that the class that comes before this, the labor class, goes into techniques that are way better for getting to that individual. They never get to individual. We don't have technology for that yet, nor do I even know that it is possible to ever have. But we do get way more detailed ability to talk about people that have way more fine characteristics than what this technology is going to yield. This technology is actually kind of bad for getting like different subgroups. Right, so we're already going from there, but it's pretty good. We do log our ITTs, they're pretty good. All right. The second term is known as the, anybody knows? What is that called? That has a famous name. What is that name? Anybody knows? Have you seen that? Have you not seen that? Anybody remembers what that is? Actually, it has more than one name, but there's one that I think is more famous than the others. You got it. Yeah, when I say you're gonna be like, oh my god, I know this. Why didn't we? Yeah, you're gonna know this. So there is two possibilities that are very famous. One of them is selection bias, and the other one is omitted variable bias. Are you ashamed now? Are you embarrassed? You should be. Come on, you know this. You know this. Okay, so the two of them are selection bias or omitted variable bias. Both of them have the reasons to be called like that. Let's even examine them because we should know this stuff. So one of them is selection bias. I like this more, it's more common these days, more modern, it's the one that's being used most now, selection bias. And the second one is omitted variable bias, OVB, omitted variable bias. Omitted variable bias. So those two names are used to that. So first, let's understand what it is, and then we talk about like why the name, because the name is actually rather interesting to think about. Oh, this name makes sense or not. Anybody? Do you raise your? No, it was just a coincidence that you have your hand like that. Okay, let me put the board there so people can look at the board. I am managing the boards way better on this one. I'm very proud of myself. You have no idea the disaster of the last class. I will get better at this. All right. So the selection bias. So what this is, first and foremost, is the thing we hate. This is our problem. This is the fundamental problem of causality. We will see in a second. But what is this object? This object is the thing that would have happened to the people that consumed one, the people that went to grad school, if they hadn't gone to grad school, compared to what happened to the people that didn't go to grad school when they don't go to grad school. So what is this? This is basically the fact that the people that went to grad school could be different from the people that didn't go to grad school. So unless you have some form of randomization, some form of something that makes these people be comparable, in principle, people who go to grad school are very different from people that do not go to grad school. And therefore, the people who don't go to grad school, the people that went to grad school, if they hadn't gone to grad school, who is to say here that they would have had the same outcome? Let me repeat that. The people that went to grad school, but if they hadn't gone to grad school, would they have had the same outcome as the people that didn't go to grad school? I mean, the people that didn't go to grad school, they're not going to be super nerds, are they? Right? So like, on average, they're going to be more or less nerdy. They're going to be less nerdy. So the outcomes of the less nerdy people not going to grad school compared to the outcome of the people who are more nerdy, but if they hadn't gone to grad school, they're not necessarily the same. Because that nerdiness transfers. It's not just to study. It also might be used to just, I don't know, be more applied at work, perhaps. Because I'm calling nerdiness, but a lot of that is basically a ability to sit down and study. And that thing is a transferable skill. I mean, it transfers to other things. You're gonna go there, let's say, be a programmer or something like that. And I don't know, maybe you are more willing to sit down and more to study and to work hard on those things. Which is not to say necessarily people in grad school work harder than people that are not. But for some employment types, I bet that those skills transfer better, right? Even if you haven't gone to grad school, there's something inherent about them. So consider, for example, effect of smoking on birth rate, which is an example I know a lot about because I've worked with it quite a bit. So if you consider that the biggest problem here when you compare mothers that smoke and mothers that don't smoke is that they're different in 1,000 ways. And in fact, in the case of this particular example, we know exactly that because we have the actual data. They are educated with an average one more year than the mother. And I'm not even talking about the mothers that smoke. I'm talking the mothers that smoke one cigarette. So basically, if you compare the mothers that don't smoke to the mothers that smoke one cigarette, they have 1 year of education more. They have the father of the child has more than 1 year of education than the ones that the mother smoked. They are married with 30% more likelihood. They're 30% more likely to be married. Y'all, this is huge. Huge difference. And, on and on and on. In almost everything, they are different. Very, very different. So when you have a difference in birth weight, was it the cigarettes or was it anything else? And that is the fundamental problem of causal inference. The fundamental problem of causal inference is that when I compare two groups, the difference in that outcome could be the treatment effect. So in the case of cigarettes, it could have been the smoking. In the case of the grad school, it could have been the actual grad school in comparison to not have done it. But it could also be the inherent differences between the two groups. The fact that these mothers that smoked would have done worse anyway, because they had other factors that would have made them worse anyway. And the mothers that didn't smoke were already positively selected in some sense, and therefore they did better. And the opposite in the case of the grad school, which is the fact that the people who went to grad school, and then let's just say that they got a better wages. Is it because of the grad school? Or is it because they were already better in some sense? They may have been smarter, they may have been more applied, they may have been more able to focus, they may have been more able to do useless stuff for a long time, which is basically what the reality of now going to college and studying things that basically AI can do for you. When right at the undergrad level, this is actually rather common, but they were willing to go through that, get past it, and then get to grad school when you get to levels where perhaps AI does not know or cannot do for you, right? So all these things are skills that could have made them money anyway, and it has nothing to do with the grad school. It just has to do with who you are in some other sense, right? So that is the problem. Whenever you compare two groups, you never know so part of the difference is due to causal effect, part of the difference is due to that, and you never know how much or even if it exists, because you could have zero effect. You don't know which proportion is due to anything, so you cannot separate. When you look at that number, it says nothing. I mean, this number could be negative and the other could be positive and it could have canceled. Like this thing says nothing. Basically, by looking at that difference, without any further assumptions or any further prejudice in your mind, there is absolutely no bound on what those values could have. That's how bad this is. It's fundamentally not identified. You need more things to be able to say anything at all, because in principle, to get any value here, you could have had any value there could have been justified by an infinite combination of values here. So absolutely not identifiable. So the fundamental problem of causal inference, I'm going to write it because anything known as the fundamental problem of anything requires some respect, right? So we should know, let's write it down. The fundamental problem causal inference can be written down as this equation, being this and this, okay? So the first and the last. I'm not going to rewrite it because it would be a waste of time. But the first and the last. So the fundamental problem of causal inference is that it is extremely problematic to do causal inference in a fundamental way. Why? Because you have an impossibility in principle to separate between what is a causal effect and what is the effect of everything else, and they're just inherent differences. That is the problem that anybody who is doing any causal research has to contend with. And it's, by the way, the first line of inquiry that you should have on any seminar. So let's say you go into a seminar when somebody says that they're examining the effect of anything on anything. The very first thing that has to be on your mind, and by the way, not first, the first thing continue, it has to be there the whole time. Which is you saying like, wait. But I mean, is that a causal effect or is that due to inherent differences? That's the first thing that should be on your mind, and you should continue all the time. You should raise your hand and ask, these are the questions that should come. There is more things to look into, but that one should always be there. It's like the first thing a person needs to explain to us when they said, I got the causal effect of something, is how they addressed the fundamental problem causal inference, which is equivalent to say, how did you address selection bias or omitted variable bias? You have to have addressed that somehow. Now, I'm going to talk about those names and why they are what they are, because that gives us clues, and also because it's interesting, you should know. But before that, let me just tell you something kind of obvious, which is that if I didn't have selection bias, if this quantity was 0, then you would not have a problem, because the comparison between the groups would be the causal effect, and we would all be happy, right? That would have given us that, which means that destroying the selection bias is what you want to do. So every form of causal identification, as far as I can understand, destroys the selection bias in some way. Randomizations destroy the selection bias by making the two groups equal and zeroing them in. Now goes to your question. Let me just come here a little bit to the camera. Now, that goes to your question, because there are techniques that don't destroy it, but try to get it. And if you get the selection bias, you can subtract. So the immense majority of techniques, the classic way to deal with it is to destroy the selection bias, to make it 0 somehow. And so let's discuss how this is done in a second, like, in general. And by getting comparability between two groups, you destroy it. And now, recently, there are some techniques that go after the selection bias and try to get it, and then subtract it. Basically, just correct for it. Which means that the causality is not, the solution to causality is not randomization, and is not even comparability. It's the killing of the selection bias. As far as I understand, the unifying rule of every method is that you need to address the selection bias somehow. That is the idea, how you do it. Okay, so now let's go to the understanding of the nomenclature, because it is important. And why do we call this selection bias? So the reason we call this selection bias is because there is a notion that we have in which, if you don't really go and do something to a sample, if you're just looking at observations in the world, everybody who has taken a certain level of treatment has decided to take a level of treatment in some sense, either themselves or somebody decided for them. The better word than decide is that they selected into that treatment. So everybody has selected into a treatment. So we could have said decision bias, but decision bias wouldn't cover as many cases. Because, for example, what is the effect of exercising versus not exercising? So you have the effect of exercise. So if you compare people who exercise and people who do not exercise, you have the effect of exercise plus the effect of the decision bias. It's the fact that people who decide to exercise, people who do not decide to not exercise are different. So there'll be a decision difference. But the reality is that not everybody decides. For example, how much TV does a child watch? Is this a decision variable? Because a child watches TV, but it's heavily decided by the parents. Because, in a lot of senses, if you watch more or less TV, is heavily determined by how much your parents let you. So the child didn't decide anything. The child was selected into that amount by somebody else, who the parents. So you see, you could even think as a decision of the parents. But you get my meaning. So, for example, there are many instances in which there's no real decision. You get selected into something. So, for example, some treatments are not really even decision variables. They're just like things that just happen to you. Let me think about it. Oh, yeah, perfect. Race. So we study the causal effect of race. Now, race is not an actual modifiable variable, and it's not a variable. Gender saying, I should like actually watch what I say right now. But you get what I mean, right? So it's not really a modifiable variable that can go there and say, oh, now I don't know what this is getting very weird these days. But it's the kind of thing that you have a certain there's a sense in which this thing is innate. Everything I say here goes wrong. Let's talk about race. So this is problematic. Okay, so let's just say somebody's born a certain race, and more importantly than even being born a certain race, you're raised in a certain race. So you basically get exposed to everything that it means to be in that race. You can't just go there and switch your history because you can't go back in time. So you can't switch your history. There's no such a thing as a treatment effect that has to do with manipulation. There's no manipulation, and yet all of you agree with me that there is such a thing as a causal effect of race, right? Which is what? Is to look at somebody with all of the inherent characteristics that are inherent to them, like personal, instead of like social, societal. So basically just who that person is. And then you think about what would have happened had that person been of a different race. So it's a perfectly good counterfactual understanding of this. We all get like, oh yeah, you can totally get the causal effect of race. This is a well-conceived question. Wouldn't you say that? And yet there is no manipulation because it's not really a manipulable variable. There is no, there's no notion in which this, and there's definitely no selection, right? Because you don't select into a race. You select it by birth, by like when the souls were distributed among the, like, there's no selection. You're just born there, right? Like if you even believe anything like that, you selected yourself. You see what I mean? So and by the way, immutable characteristics are some of the most studied topics in economics. We study discrimination, we study segregation, we study gender gaps, we study all this stuff all the time. In every single area, we study that in crime, we study in education, we study them in wages, we study everywhere. Those types of topics, right? It's like hugely important sociologically speaking, and this is a social science. So we study all this stuff all the time, and those questions are fundamentally non-manipulable, right? Non-decision characteristics. So I think it's pretty interesting to realize, which is why the word selection bias is actually a pretty good one, because it talks about the inherent differences in the way people have been selected. And you may have been selected by yourself or by somebody else or by nature in some way, right? So you are selected into that particular characteristic and so on. And so the idea here being that when you compare classic economics issue, right? We want to know if there is a gender gap in wages, right? The classic 30% gender gap. So there's a 30% gender gap, which could be due to the fact that there is some form of discrimination in which women end up paid less. But there could also be inherent differences between women and men. And many things have been proposed. And the fact is that when we look at general current state of science in economics, we more or less believe that 30% of the 30% difference observed in nature of 70% to a dollar, 20% are due to this sense. Basically, we're discussing around the 9 to 10%. Right now, this is definitely a contentious area still. We don't really know that stuff, but we're looking into like 9% here, true gap. It is true that we don't destroy that gap, meaning so far as we understand, there is something, but it's of the order of 9-10%, not of the order of 30%. It's a good 20% are explained by things that are inherently different between women and men, which is not a moral statement. I'm just saying things like, I don't know, they may have the classic explanation, the one that accounts for most of the stuff is a choice of profession. Is that women heavily go into professions that are actually lower paying than men. Now, that again could be a societal problem. Why do women choose that? And then we can discuss that, blah, blah, blah. But it's not a problem of the company. You can't fault the company for that. The company may be paying right. You see what I mean? Like you can have a company doing everything right. You can't help it that this is a hospital and these other people are computer scientists. Heavy STEM fields or something like that. And the women are, much more likely to be teachers, much more likely to be nurses, much more likely to be all these things. But you know what I mean? Can it be a social problem? Yes, but it is actually from the perspective of the company, like, well, the company is not doing anything wrong in principle. You get it? So the basic idea here is that we have a question that is not a decision question, which has a problem of selection bias that is well known. And the word selection is actually a good one because it's an immutable characteristic. And it is, you see all these factors. Now, the other nomenclature, which is the omitted variable bias, is also awesome. Because, so much older, much older. This is actually, used to be the most common one. I used to teach undergrads, and I used to teach, I still teach undergrads. I used to teach undergrads with omitted variable bias. Nowadays, I teach selection bias because it is dominating these days. But omitted variable bias was the dominant terminology for a long time. And it is actually rather excellent because it gets at a different issue. So they're both kind of like, the telltales of something, and I think it's pretty neat. And so let's look at omitted variable bias. So let me just not do that yet. So omitted variable bias, that nomenclature has to do with the most important reason why you have that bias at all. The most important reason that we have that bias at all. So first of all, why do we have that bias? We have that bias when the yi's of 0 of a group are different from the yi's of 0 of a group. And the next question will be, why might they be different? Why are they different? Why is the y of 0 different than the other thing? Well, the most intuitive, fastest thing our brain goes into, and I still believe the most likely to be happening, is the fact that we have different characteristics. Is the fact that there are things about you that are inherently different. And so those things are variables, first of all. And so they're variables. And they're variables that have a name that I actually love that name. I think it's highly explanatory. And that name is confounders. So we're going to talk about confounders right now. But the idea here is that why are the women who smoke inherently different from the women who don't smoke? I said to you when I was explaining that case, I said they are educated 1 more year. I said they are married, but 30% higher likely. Right? I said things about them. So there are things about them that make them different. Those things we're going to see in a second. It's a little more complex. And I don't even know if I can get there today. I might. I don't know. But those things are what we're going to call confounders. I'm going to define them a lot better than I'm doing right now, but in your head, you already kind of get it, right? So these are going to be fundamental systematic differences between two groups that are happening, that are causing those inherent differences that have nothing to do with the treatment that would happen anyway. That's kind of like what it is. Confounders are our enemies. Our monster that we have to defeat is selection bias, and confounders are like, the minions we have to attack. So in a sense, in this war, confounders are the end. That's basically the idea there. And the way that this used to be done the most, and by the way, it's still done quite a bit, is by running regressions and controlling for stuff. And so what do? You have to control for confounders. And so when you control for confounders, you hopefully have solved it, unless there are still variables that you did not control for. And the variables that you didn't control for, you omitted, which is why you have an omitted variable bias. So the context of omitted variable bias is the context of regression, which is why it survived so long in undergrad and why it has been killed in undergrad level and science level, because we're not doing that as our fundamental way to account for endogeneity anymore. So because we're not doing that anymore, we're like a lot more in this world of selection stuff. But the undergrads are still doing regression courses, because regression is still the single most used technique everywhere. So they need to learn regression well. And in that context, omitted variable bias makes a lot of sense. So that's kind of the reason for that. But I like omitted variable bias exactly because it gives us that notion of selection and the fact that had you been able to observe things, had you been able to make comparisons, controlling for things, that you might have solved those problems. So that's the reason for omitted variable bias, okay, for you to know. Now let's talk about confounders. So let me take the board there. Let's talk about confounders. Wrong person. Okay, confounders. Any questions so far, by the way? Anything? Are you bored yet? Yes. I want to see who's brave enough to tell me. I'm bored. Shut up. All right. So, okay, confounders. So the first thing to think is confounders are variables, okay? So confounders are variables that confound us. They're variables that confound. And truly, the sense is really great because you go to the fundamental problem of causal inference, that decomposition, and they are the thing that confound us, right? It's literally, it's a greatly different thing. Now, confounders, just as everything else causal at the root, is not properly defined. It does not have formal standing, does not have a mathematical grounding. So I'm going to tell you what characterizes a confounder as much as we can understand, and I'll tell you good luck. Because at the essence, there is no mathematical definition of confounders, because to define a confounder is to define something that would break counterfactuals. But I mean, then you have to you see, like at the essence is going to it's tautological. It's it's what breaks the counterfactuals, but then what breaks the counterfactuals is whatever breaks the counterfactuals. They're defined by principle. So what is a confounder? First of all, a confounder is a systematic difference. So it's a difference that occurs between the group of treated and untreated, or whatever comparisons you make. So in our case, right now, this class is going to be treated and untreated. It's going to be difference between so it's a variable that causes differences in yi of 0 among treated and untreated. Okay? So that's the first thing. So confounders are variables that cause, even the word cause here is problematic, cause differences in yi of 0 between treated and untreated groups. So that's the first thing about what confounders are. They have to be, so for example, if the women who smoke and the women who don't smoke consume in average the same amount of Coca-Cola, Coca-Cola is not a confounder. The first thing, you need to be a systematic difference, right? So you have to be, first of all, systematic difference. It has to be different across the two groups. And also, you also have to affect the y of 0. So there's two pieces here. A confounder must be systematically different. So I have di equals 0, di equals 1. I have to have difference. So I have to have, let's say, I don't even know how to write this thing, but I need to have more Coke. I don't even like to say Coke because it looks like it's the drug. Have more Coca-Cola in one group, less Coca-Cola in a group. So first of all, it needs to be a variable that is systematically different between the two groups. First. And the second thing, that variable has to affect somehow the outcome. Because I could also have that one group consumes more Coca-Cola than the other, but guess what? Coca-Cola doesn't affect the birth weight. Now, does Coca-Cola affect the birth weight? I don't know, man. I mean, excessive sugar consumption might a little bit, especially if I don't know, but it's less than you might think, actually. Yeah, less than you might think. But you get what I mean here? So you know what does affect alcohol? Alcohol is a great confounder. Why? Because alcohol is a variable that is very different between smokers and non-smokers. Smokers do drink more. So that is a fact. We have data for that. And the studies seem to show, actually much more conclusive than in the case of smoking, that alcohol does affect the baby. Mind you, there might not be a birth weight though, but it does affect brain development and things like that if consumed beyond a strong level. So alcohol binging is heavily bad. Alcohol per se, not necessarily, depends on what, but I mean, the research shows that binging definitely is very negative and high alcohol consumption is bad, right? So we know that, and it's better established than smoking itself. But you see, you get my meaning? So it has the two components. So we have to have the two components. Don't miss that, okay? So confounders, I don't like this because I don't even know how to write this. Confounders must be different, must vary across the groups, And when I say across groups, I mean treated and untreated. Across groups. And must affect outcome. Now, do I mean must affect outcome in a causal way? It must cause the outcome. No, not necessarily. No, not necessarily. I just mean that y of 0 differences can be correlated with it. So you don't have to have a causal relationship for it to be a confounder. But you know what? Very commonly there is. And it's actually very cool when there is, because it is a lot easier to think about. But there are examples against that. Now, that is all necessary. Those are all necessary conditions for confounding. They're not sufficient, meaning, what do I want to say? So they're all necessary conditions, but that's not enough. A confounder must also not only have all these characteristics, but also a confounder must not be predicted by the controls. So in the context that you are using controls, then it should not be predicted by them. So let me just write that down because that completes it. It's not really relevant for this course, but I cannot define confounder without telling you that because I'll miss something really, really. So must not be predicted. And by predicted, I mean like well predicted, right? Predicted with like mean zero error. Predicted by the controls. So like well predicted by the controls. What do I mean here? Drinking. Is there a potential confounder? By all means, yes. Is it a systematic difference that affects that would affect the birth rate? Or at least we think it could. But is it predicted by the controls? Well, I do have drinking in the data set, but the data set that has smoking tend to have drinking. The most important data set for observational research on smoking is the natality file. So the files that they're collected with hospital data at the time of when the child is born. So they get the birth certificate and then they get all the information from they connect it to all the information from the hospital. It's pretty detailed information on smoking and also on drinking. So I can control for drinking. When I control for drinking, do I have a problem? Is this a confounder? No, this is not confounding anything. I'm not confounded by this because I am controlling for it. I am now comparing. So what do I do? What does controlling mean? Controlling means that instead of comparing smokers and non-smokers, I am now going to compare women who smoke and don't smoke, but who drink exactly the same amount. I'm going to go, women who drink exactly the same amount, comparing smokers and non-smokers. Do I have a systematic difference? Do I have systematic differences between these two women? Yeah, I probably do. Because it's just, I'm just saying that they smoke, that they drink the same, but they still probably have a lot of systematic differences. But do I have a drinking difference? I don't have a drinking difference. So I can have 99 problems. Drinking ain't one. So there's one of them that I don't have, and that is the alcohol. Right? So by controlling for alcohol, I took care of that one pesky little problem. Therefore, it is no longer a confounder because it's not confounding us. It may be confounded by other reasons.
Like those two effects could be affecting each other. Like the people who are the women that are drinking and smoking, maybe those two things doing together.
Yes, causality.
Yeah.
Save this for a second. Not sure I get to it today, but I will talk about this. What you're talking about is a mediator. Yeah. So you're talking about the problem that we have fundamentally opposed determining variable because drinking, or at least jointly determined. Because the fact is that you don't it's not an inherent characteristic, it's something that's sort of determined at the same time. Because you're drinking and smoking and making that decision and kind of like mixing it up, and one of them causing the other all the time. And that's confusing as well. We'll talk. This is probably the next topic. I just don't get there today, but I'm going to get there tomorrow. Definitely an issue. Hey, shall we for now? Yes.
Also, wouldn't you consider if drinking was to be a confounder, the other factors could be used to predict if somebody would be drinking or not?
Yes, exactly. Let's talk about this right now because I was going to talk anyways. The next thing. Okay, so I control for smoking. Basis of causality based, how do you get causal effects with controls? So the idea is that I'm not going to control just for drinking. So the hope is that I have a very large data set and that I have drinking, I have education, marital status, the education of the father, I have prenatal visits, I have a whole bunch of health characteristics, and everything I'm telling you are things that actually exist on those data sets. You have all this stuff. And so every single thing you control for is no longer a confounder, because if you are predicted by the controls, you're no longer a confounder. But here is the beautiful thing about the world and the predictability of humans, which is the fact that if I know one thing about you, I might just know that one. But if I know two things, I know three. If I know 5, I know 100. Because the fact is that people end up boxing themselves. Suppose that I tell you that somebody is favorable to trans rights. I literally just told you one thing. Next, likelihood of being a Democrat. It's like, you kind of know, right? Right? And the same thing against, right? It's almost like, and perhaps not that, because perhaps it's like too controversial an issue, and there's a lot of dissidents even among Democrats. But now I told you that they are about that, and also they have an opinion on ICE, and then I gave you another opinion on some other thing like that. I gave you like 3 things, and you can tell Democrat or Republican, right? And when you can tell that, you can tell 15,000 things. Right? Isn't this the world now? So, and I'm not saying, I'm saying everything I'm saying, I would say Republican. What I mean here is that when you look at controversial issues, and by the way, this is not really a thing I'm just saying, this is really a fact. So part of Greg's research, they established exactly that. There were, in controversial issues, you could ask 2 questions were sufficient to predict basically every other question. So in all of those controversial issues, generally speaking, 2 issues already tell what is going to be your opinion on pretty much everything else, which is kind of incredible and also sad, because it shouldn't be like that. You should be less predictable, right? People should have, more varied opinions. But the reality, unless you're like that and you're like, blasphemy, you should have my opinion. And then both sides can say the same. But you get what I mean? You get the idea, right? So the idea is that the more you know about somebody, the more you know about what you don't know. Because then you're like, but the classic thing of that is like Netflix prediction of how much you're gonna like something. Don't you like? Isn't it amazing? I think Netflix is pretty good. Maybe I'm like too predictable, but Netflix is pretty good. When they put like a 90-something% on something, I'm pretty likely to like it. Like when they put those numbers. How do they know this? Because people like you also like that. So what they do is that they look at people that, okay, you watch this, you watch this, you watch this, you watch this, and then you like. You don't watch those things. You look like the people who do this. Therefore, I'm kind of predicting that. And guess what? They're kind of right. So most of the time. So the idea is that you can then infer about things that are not there. And that's how you do it. So basically, the more you control, the more you can predict things you don't even observe. Which is why with a whole bunch of characteristics, you might be able to predict drinking. Or you might be able to predict other things that we don't observe. For example, in the case of pregnancy, a huge thing I would imagine, which determines the birth weight of the child, is going to be very important, is how desired that child is, how invested the mother is on that pregnancy. Because that's going to determine the quality of her nutrition, which is a heavy determinant of birth weight. So that's kind of the biggest thing I'm after is nutrition. Now that data does not have nutrition, but I'm hoping with all these controls, I can get a nutrition. The spoiler is that it doesn't, so it's not enough. But that was the hope, and very serious applied research has been done, which already decreased the bias substantially, trying to get at that nutrition. Did they get all the nutrition? No, but they got a substantial amount. That's kind of like the basis of causal inference by controlling. The idea is what? I'm going to get at confounders until they're no longer confounding us. Everything I get at is not a confounder. So you are a confounder only if you fail that. So a confounder, by principle, must be a problem. It must always be a problem. Because the moment you're no longer a problem, you're no longer a confounder. So if I say this is a confounder, that means I have no control for you, right? So you were a potential problem, and then I did not control for you. So it's trouble. So that is, let me just finish up. So that is basically the confounder definition. And then just so you know, this is not the only type of problem that's going to cause systematic differences. We're going to discuss some others. And you had a great example, like you were talking about like the joint thing. That's going to be a mediator problem. That's sometimes an issue, sometimes it's not. We can have also collider problems. So there are other issues that are going to cause problems, selection bias. But the most famous, the most important, I would say probably the most likely to be the issue indeed, is confounding. It's the fact that these people just have different characteristics from these people, and until you control for them, you don't. Okay, so that's the idea. And then every technology that's going to go after causal inference has to account for this somehow. And what is the way that an ideal experiment would account for it? By randomizing perfectly and making those groups be equal, these things going to cancel out, and then you will get what you want. That'll be the idea. Well, IVs, RTDs, they're going to do more sophisticated things, and they're going to get rid of this thing some way or another. Bunching is going to go after actually identifying that term and then subtracting it out, and so on. You get what I mean. Now, the way that controls do, so the classic way, is that you would basically just fix those characteristics and not look at subgroups, treated and untreated. You look at subgroups within characteristic set. So I'm going to look at people who have the exact same income, marital status, race, all these things. And then I'm hoping that when I get all these things fixed, these people are indeed comparable. The y-zeros are comparable, and then they cancel out. That's the idea of control. Every technique does it somehow. And I'm going to give you a little bit of a tour of what each one of them, how they all do it. I'm going to go into what I do does. Okay. But that's kind of the baseline. And that's it. All right.